All right. Okay, it's 9:55. Okay. So, uh, let me admit a few more people in. Hi Hafiz, I've already unmuted myself. Can you hear me? Can everyone hear me? Perhaps give a thumbs up. Okay, yep. Hello, okay, good morning. Okay, so yeah, as I thank you. Okay, thank you everyone. Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning everyone. Welcome to our second National Training Week 2026 session. It's wonderful to see familiar names returning from our first session last week. To our returning participants, welcome back. And to those joining us for the first time, we're delighted to have you with us. Today's session, Behind Every Oil and Gas Project, Understanding Field Development Planning and Project Execution, will provide valuable insights into how oil and gas projects are evaluated, planned, and executed from discovery to production. So the session will once again be delivered by our experienced trainer, Mr. Latif Matesa, or as many of you may know him fondly as Cikgu. Okay, before we begin, just a few housekeeping announcements for participants registering through the NTW portal. Your e-certificate for our previous session is now available. Just simply log into your NTW account and download it directly from the portal. Secondly, we also pleased to share that all our NTW sessions are being recorded. If you would like to revisit the session or share them with your colleagues, they will be available on our Fazmia Technology YouTube channel by the end of the week. Do subscribe and stay updated with our latest technical sharing session. Um, then next one is the for latest industry insights, company updates and information on our upcoming professional training programs. We also invite you to follow our Fazmia Academy page on LinkedIn. Okay, lastly, I will be sharing a QR code for our attendance and feedback form. Please take a moment to complete it before today's session, the end of today's session. This is especially important for participants who registered through the NTW portals. Kindly use the same name and email that you registered through NTW to ensure your attendance is recorded properly so you can get your certificate. Okay, without further ado, it is my pleasure to invite our trainer, Mr. Latif Matesa, to begin our today's session. Cikgu, the floor is yours.
Okay.
Ah, okay, so today,
Okay.
start balik.
Okay, good morning, everyone. My name is Latif, or you can call it Cikgu. So today we're going to cover a very interesting subject, we call it critical subject in oil and gas. And we call it understanding field development planning and project execution. So we're not talking about only development planning, but the execution part of the subject. So hopefully, as you know, we're going to go through very quickly And because we have quite a few slides, we might be extending our session here, maybe another 10 to 15 minutes. Hopefully, we can cover enough time. So please bear with me. And of course, to you know myself, actually, I have been in the industry for about 40 years in oil and gas, and covering mostly the upstream sector. And you can see also actually before my retirement, I'm holding the title of subject master expert in well drilling engineering. So of course, assignment itself, I'm a senior engineer before during my early age, early 10 years, 15 years in oil and gas. I've been working with various company in Gulf of Thailand, Sarawak, and of course in Saudi Aramco. So I have the opportunity to spend my time about 5 years in Saudi Aramco on extensive onshore drilling for oil and gas. So this is also where I am covering about HPHT, with temperature is very high and also pressure about 11,000. I'm not coming across anything up to 20,000 PSI yet. It's only the later session when I joined Petronas at the last, I think the last 10 years. Actually, I had the opportunity to see how they're planning for very high pressure, like 15,000, 16,000 PSI. Okay, I have been working in well intervention in Sarawak 3 years, and of course in Malaysian Thai joint development area, which is there about 4 years, and of course 5 years in Saudi Aramco. So also I've been involved with field development plan and with doing strategies, project economics, risk assessment, and so on. So in terms of overall exposure to oil and gas, I've been doing the HPHT well, the urban drilling, workovers, well services, and ARD wells, with Talisman. HPHT, of course, going to be in Aramco and of course in Malaysian Thai joint activity, where we drill gas deep down up to 400 degrees F. And then, of course, coal turbine drilling, actually part of my exposure, my planning team with Saudi Aramco, going for coal turbine drilling with Schlumberger as part of the key contractor. Deep water, I'm not directly involved, but I'm one of the I call it the reviewer for the plan. So I review most of the deep water planning in Gali and give the approval on the costing and the dish for each well. Carbonate drilling coming from Sabah Sarawak and weapon A. Hollywood October, I'm involved with both Pride Carigali and Talisman in Malaysia. Okay, so for the content, we're going to go to about 7 modules: geophysical, geological, reservoir, production, development options, front-end engineering, and the project economics. So we go through more likely the briefing, very briefly on each subject. And of course, the importance of the understanding is that, when you see through the slides, there is a content and the facts or the keywords that you can use those keywords in your search for more information to AI. Can go check GPT or maybe for the Copilot and all those DeepSeek and all other AI to explore more. But you need a keyword, so I'm providing you the keywords in most of the on each slides that we're going to present to you. Okay, let's start with introduction quickly. What do you have DP? It's a subsurface business plan. And of course, we're going to have a strategy how to produce and evacuate hydrocarbon in the most cost-effective and safe manner. So if it's cost-effective but it's not safe, you're going to expose your company into danger. But if it's safe but not cost-effective, it's going to be a loss to your company because running a very poor planned project. So we must have both, cost-effective as well as safe manner. And that what we call it professional work. So we are as professional, we are going to do that and to meet the requirement of our company to make sure that it's cost effective and safe. Okay, so at the same time, you know that when we deal about this situation of FDP, we are talking about how to decide on the reserve of the field, the recovery factor, the of course the revenue that we have yearly, some revenue declining, but still in within the good profit margin, and so on. So of course we're going to evaluate how the project capex and OPEX. So capex means capital expenditure. OPEX mean operating expenditure. So there also be another OPEX for production, and we're going to compute the net cash flow for the project and see whether it's going to be positive or negative. At the same time, of course, all this will cover under the economic study and the economic indicators, the risk factors involved in the project, and the mitigation that we should put in place to be able to handle issues that is coming in on the way, within the field life of the project. Okay, so for the field life cycle, you can see that we have about five sections: acquisition, exploration, development, production, and abandonment. So these phases is covered the field life cycle. So normally we call it conceptual FDP during the acquisition exploration. Then once we confirm it's a feasible project, then we talk about the final FDP. We go to development, the production process, and the abandonment plan of the field before we leave the area. So all this cycle can go from 15 years to 50 years. Sometimes it go beyond 50 years. So some field in some area is going to be more than that. So in terms of the PAC, normally PAC will cover about 25 years. So any field extension, and of course we can ask for extension for FDP out of the PAC to cover another 5 years each or another 10 years based on the government approval. So first of all, acquisition of the area, like we're going to secure a block. There will be some bidding process. So national oil company like Petronas, of course like uh, Thai authority, maybe the Vietnam oil company, or maybe Indian oil company, and so on. They will invite for a bid for the block in their country. And of course, when we come into a project, the project is quite expensive, especially for deep water, HPAT area or remote area. Normally, we ask for partner so that we can share the risk of losing. So, we distribute risk by having a partner rather than holding 100% share. Normally, we start to split. This always happen in oil and gas because it's a high risk, high reward investment. So the risk itself should be shared with other partner, and then we learn each other, because sometimes when you have partners, the partners will be your support or your community or your partners to really help you to make a very right decision, even to support you in some technical or logistic requirement. Okay, so of course, when sometimes you go for bidding, you go on your own, or sometimes you go as a partner. And of course, open block bidding is interesting, when you come in with your expertise, with all your knowledge, and try to bid for the best price. So once we have that in Malaysia, you have to assign, it's going to be assigned by Petronas for the bidding process, and then who is going to be winner for that block. Okay, for the second process on exploration, you can, once you have acquired the block, because you're going to go for the seismic acquisitions, you're going to be, and then you have to be processing the seismic. You have to decide on the trap or the carbon source from that particular information from the seismic. And then once you have some idea about the potential, then you start to drill one exploration well, or we call it wildcat well. And this well, we did actually go through all the expectation, because before it's only mapping through the seismic, but now you're going to go with through punching through the formation, getting to the properties, getting to the fluid, whether it's going to be oil, water, or gas. As you go as deep as possible. Normally, exploration well, we go to the basement of the area. So basement means that after that you're going to be hitting very hard formation, and it's difficult to drill. This is exploration well. Then once you drill exploration well, then you can see that there's another uncertainty about the extension of the reservoir or the field. Then you might be drilling appraisal well to confirm the extension of the field. And then there's also at the same time you get more information with your logs, with your core, and of course with your other information about drilling. Yeah? You know how fast you can drill, what are going to be your issues of drilling this well. All they will be covered under appraisal well. And of course, in the appraisal well, you have logging and coring. You're going to do production testing to know the potential of each reservoir. And then you establish the project economics before you decide on whether you're going to proceed with the development project. So for the development itself, you can see that you're going to evaluate all the data that you have from the exploration part and appraisal. And of course, you have to go for the regional area, understanding what is the regional experience, any relationship with your field, then you use the data, offset data from the field to help you to make a better decision. So you develop the FDP, and of course you're going to go for the life cycle, means that you have to understand the cost involved from start to the end of the field. So all the phases that you've seen below here will be covered under life cycle cost. And of course, when you produce from the reservoir, we have to develop a strategy, depletion strategy, and the reservoir management plan. So reservoir management plan actually is the intention to really make sure that we maximize the production and optimize the reserve that we're going to recover. Okay. So in production itself, you can see that for production, it's a stage where we already built the platform. We have already have the pipelines, and for the well drills, then we're going to produce as per the reservoir management plan. We monitor the production, with the water production, we monitor, and of course, how much gas being produced, how much oil being produced. So all this will be covered in detail so that we can compute the total potential of the field, then have the optimization done. All this will be covered under production phase. Okay, finally, of course, we're going to once the economics of the area, for example, you're producing too low, and then your of course your expenses is high. It's time to end the project. We have to more or less uh, close up our investment, and we go to abandon the field. And decommission means that we clean up all the pipelines, all the structure, so that it go back to the original or its condition. Normally, it takes, like I mentioned before, it can be 20 years or it can be like 50 years before you start to think about, field abandonment and decommissioning. Okay, so the next one is the FDP process. This is quickly we go to the FDP process. Same thing, opportunity and acquisition, then we justify by FDP through the FDP study. And at the same time, we're going to do the economics. If it is okay, then we talk about going straight away to initiate the FDP, then continue. If it is no, it's not economic, then normally it's not going to be just give up away. So we have to go with another situation of understanding what can we do to make it economics. This is where we go and explore the technology available, and then of course we're going to assess the technology and go back to the study. And the study show that actually you improve your economics, then you go and proceed with your FDP. So the technology here, you can see that there's a lot of thinking about how we should develop the field with a different style, like a marginal field have a different technique that to make it economics. If it is big field, of course, it'll be a challenge to reduce all the uncertainty of the reservoir and so on. So when you have done that, after you want to go for initiate the FDP setup, you're going to prepare a reservoir modeling, and then you have to select the best option to develop the field. That go back to what we discussed before in terms of technology and so on. Okay, so once you're done, you're going to see all these options that we have. If it is economic, then you're acceptable. You start to prepare for your implementation of the project, get the budget, get whatever preparation for the team they're going to prepare for the planning. And of course, there's going to be a review on the final field development plan project. Okay, so that's the more or less the cycle of FDP process. Okay, so in terms of the message, what are the kind of people that we need? Because FDP, as you can see, is covering from a very few five sectors, from exploration, and then talking about development, and then to of course all this FDP and so on, this PNA and so on. So FDP is developed through multiple screen. You can see that we have about five. But same thing, we have the free data and setup team here, that the team here should be doing the job to gather information, and then let's do the static modeling, dynamic modeling, and then of course select the development option and do the front end engineering to build up the facilities, the platform, the pipeline, and so on. So you can see, well, at this page you have sometimes a subspace manager that will more or less manage the project, for these phases here, and this is a transition. Project manager will be also covering all the development field plus the construction of the facilities. Okay, so now we can see that for the people involved, normally first phase geophysics and the geologists involved. Geophysics is going to be the seismic, geology is going to be with the static modeling. And then petrophysics, we have to improve, because we have some data on the rocks. So petrophysics will evaluate on the rocks properties at the same time the geomechanics of it that will help us to build up a good we call it uh, the origin, how the field looks like. And then, of course, production technology we get involved with the engineer. And then it come to the development where we have facilities engineer and economists to come to work together to really make sure that we complete the project successfully and is ready for production. Okay. And then for the geophysical, this is the first start of geophysical project. We have, for example, for the process itself, it's going to be that's more or less the same process like we discussed before, the data availability, then we do the seismic well tie-in, then we interpret the seismic and mapping, and then we do the velocity modeling. Because most of the mapping here is by time based, by time. So millisecond versus millisecond. But when we notice we're talking about converting those millisecond to meter or feet, then we can see the thickness of the reservoir and how deep, where is the depth of each reservoir. So the conversion is important here. Then we prepare a structured map and do the static modeling. Of course, we go to dynamic modeling later on. But for this geophysical, this is static modeling is the target. You can see that most of the information from seismic interpretation here is going to go through and forth. The acquisition impedance study, process distribution, put input to this process here, as well as the attributes and the fault. All will come into the seismic interpretation to compute the potential reserve, or they call it GRV, gross volume for the potential reservoir rock, and then they come up with the potential volume of the reserve for relation. So in terms of all this process here involve simulation. You can see that it come up with all those kind of graphics, mapping, and so on. This is a 3D graphic and so on. So you can see all this like we call it the seismic data, how they compute and they correlate from seismic and well that been drilled, exploration well, and the geomodeling more software being used. And of course, all this calculation during the process of geophysical is going to be critical. Okay, so reflow seismic data, you can see that when they have a seismic, this is the well drilled before. For example, this is the exploration well. They get some good result with all the potential of hydrocarbon in the zone here, and then they drill appraisal well to see how far it's going through. So they have 2 point data here. They will try to see the size. Before they cannot imagine how is the extension of the reserve. But with the seismic interpretation processing with the wells, they can more or less understand the how big the reservoir will be. Okay, and then of course, one they do that they have a cross section about 800 meter, which is around this the cross section. We can see the plan view, and this is one well. This is the exploration well. This is the development well. So this well itself will help them to really understand the total field as a whole. Okay, so of course, this is the seismic two-way time depth conversion, where from all these offset wells and the well that they have drilled, they can identify what are the conversion from the two-way time in millisecond, and this is the TVD of the reservoir. So when they do the planning, of course, they can see the depth. They can put the depth rather than the timing to the WT. So this is the depth in meter. And this is the well drill, and they correlate with the seismic. So the well tie-in and seismic helps the seismic to give an indication on how to interpret each layer. For example, the well that we drill is giving us the true result of formation types, the porosity, the permeability, the porosity, and some of the hardness, and of course some other elements of fragile of the, we call it going to be a solid rock or going to be a fragile, solidated, unsolidated, and so on. So they tie into the seismic, and from that information, normally AI will be used to really analyze the information of how to correlate certain portion of the seismic with this tie-in. So it will improve the quality of the seismic by having the well tie-in. So if you have only one exploration well, then of course the accuracy is going to be within range. But the one you have the second well, you have a quality check by the second well, and you have a better results between interpreting the seismic to give you more clear result because seismic give you an overall field understanding. Well, going to only a small area of coverage, but seismic will help you to understand the total field coverage in terms of the potential or potential trap and any remaining hydrocarbon. Okay. So for seismic interpretation, they can see they start to identify the potential reservoir on each layer. Because they have our geophysicists, they have expertise to see when they tie in with the well, what are the layers that they can see from the exploration well, and what are the layers they can see from the air pressure well. They can predict, they can put a virtual well in any center here and try to to interpret what are the interval of reservoir on each one. So that's the beauty of having a well tie-in between seismic and the well that they drill. Okay, of course, once we have that, this is the from, let's see, west to east, this is north to south. So there's the different cross section. So you can see it's like a cone, like a dome, where, you can see from each side is about the same size. Okay, so once you have that once you have the interpretation, you're going to use that for your static modeling, and you can start to see all those in depth at the top of the carbon or the layer and so on. So this is how we interpret from the seismic to identify the top of the reservoir, and then of course how many reservoir that we have for that particular field. Okay. So velocity model is another area where they use velocity itself to really go through with the potential reservoir on all the potential thickness of the reservoir as well. Because once you have the velocity, you have depth in meter rather than millisecond or the timer. So that will help you identify the total this gross bulk volume of the reservoir. So the gross bulk volume means that is the total volume without considering what going to be the in terms of the clay content or whatever the water content is going to be just a volume. But of course, you are going to have to find another way to see where is the level of water, what's the height of the water, the oil, and of course the gas, if any. Okay. So, of course, this is example of how the seismic show you in terms of the contour map. It's going to be like contour map. So, it's the top of the hill, and this is the end of the hill. So, it is like a dome. So, you can see that they have the exploration well, they have the appraisal well. So, this is the same position before. So, when you go to the base case, the base of the cabinet is how it looks like. So, normally for us, it's quite difficult to understand these features, but our geophysicists and our geologists, they are aware of this potential what call it, fault within the field, because some fault is isolating the hydrocarbon between on one side to another side. Some fault is not sealing, so you can see the oil, the hydrocarbon communicating from one side to another. So it's all been studied whether this shape of fault is sealing or not. Okay, so in terms of the petrophysics, they're going to study the core as well as from the logs and try to see the distribution of porosity percentage. They still start to learn about the rock properties and the core depth. So it's the core that they have, they extrapolate all the core studies on each one. I mean the porosity. So you can see the distribution is random. So that's why it's quite difficult to find an average of a certain porosity. So this is where talking about, is a normal average, a weighted average, or a different type of average to consider all these differences. It's going to be quite difficult. That is where we call it uncertainty. Porosity can be very low and can be so very high. At the same time, we're also going to evaluate the formation pressure. Formation pressure will give us the strength of the reservoir to be able to produce the hydrocarbon naturally. For example, sometimes you have a good water drive, strong water drive, so the oil can be produced for some time, for example, about 10 years with the natural drive. Sometimes you have the gas drive, the gas cap that can push the oil up for at least for the last 5 years without any need for additional water injector or gas injector. So the pressure profile is important. Another important thing about pressure profile is the identification of the gas water contact. In this case, it's gas. So what happened? This is the hydrocarbon. This is mostly the we call it the hydrostatic of water, and then you see a deviation. The deviation is steep enough to show that it's in the gas zone. This is how they will use this particular formation profile to identify whether it's gas or oil in terms of by the gradient. Okay. Of course, we talk about geophysics, they go even detail. They go for this core CT scan. CT scan is used in our medical, but of course in oil and gas, this expensive technology also being used to really scan the rocks and see more details about the detailed features, details, what call it, structure within the rocks, so that we can see whether it's going to be a good rock, a strong rocks, or fragile rocks with good porosity, or good permeability, or otherwise. So this is from CT scan. And of course, different boxer, different core depth, we have the same analysis with this CT scan. So we use technology to do that. So the module number 2, we go for the geological study. So also you can see that we are on the second stage here. We are talking about from the field data and then we are static modeling. So it's about here more or less. Okay, so for the static modeling evaluation, we need to have the data coming from the core, the IDST, from the logs, from the logging. This is we call it this time test, more or less. And then we're going to decide the project name or the references. Because references is important because whenever you use map, you must use a total coordinate. So when you shift from one area to another or one period to another period, one analysis to another analysis, we must use a same geodetic datum. So that's more or less the importance of having some good references is maintained properly. So import data, offset well data, even from nearby field. Sometimes you'll be able to get some data from the nearby field to get more correlation in your study. Structure modeling will be done by Petrel, more or less. Facies model normally be done by our geophysicists. Properties model also by porosity and permeability data and so on. So net to gross and the NGV module that we talked about will be assigned for this particular study. And it will also cover water situation, and of course, this is the criteria they use in the evaluation. Okay, so the formation volume factor also important because formation volume factor will decide what is the volume that you will have at surface. For example, you have 1,000 barrel of oil at your reservoir depth of, let's say, 10,000 feet or 3,000 meter. But what is the 1,000 barrel will happen at the top? So because you have a lower pressure and so on, normally you have a factor of like 1.02 or let's say 0.9. So it's going to be less volume, slightly less for oil. But gas is different. You have, for example, 1,000 equivalent to 1,000 barrel of gas at 10,000 feet. You might have about 800 times, 600 to 1,000 times sometimes at the surface. So as gas is expanded, but oil is a little bit shrink at the surface. Or sometimes for oil, we can say almost like 1 to 1, but actually it's slightly like 0.98. There's some shrinkage of the oil. But for gas, it can be multiplication of 500 to 800 or 1,000 even for expansion times. Okay, fluid contact, to understand the source assessment. And of course, this is the important critical part is understanding uncertainty and sensitivity of all the elements that we discussed. Because you know that in some cases, like some volume is very big. So even a slight change of, let's say, 2% different on one area, or let's say 5% changes on certain parameters will affect your volume significantly, even your profit. Okay, so for water saturation model, normally this is a popular J function being used by the oil and gas. Of course, the new suggestion is always using a different factor, but this is the common function for our water saturation. Water saturation means that you can identify what is going to be. For example, the water saturation is 60%. So the 40% is going to be either for gas or for oil. So that's more or less the understanding about water saturation that we tell you what is going to be the volume of oil and gas of the reservoir. Okay, this is typical, we call it regiment sediment. You can see for this field, you can see that is this is the fundamental, the seabed. What happens is the scale is very big difference. This is, let's say, a very big scale, about 4 kilometer scale for one spot, but you have 4 kilometer on all. So you can see that a big difference. So you expand the top, the x-axis, very big. Well, then you can expand it, for example. So what will happen to all the features? It start to flatten up. So actually the field is almost like a flat reservoir, just a slight height in terms of the elevation. But if you compress all this into a small scale, like this one from the x-axis, you can see it's just like a hill. Actually, it's almost flat with the gradual depth if you go for scale. So in this particular case, actually, there's a build of we call it this growth of coral. This coral grows. The coral grows becomes so huge when it is actually around the seabed before, and then later on it being all the sediment is piling up to surface. But before the original of this coral actually coming from the seabed before the earth being it being replaced with all the depositional sand, shale, clay, and so on at top. So this is actually a source. The area the reservoir they become a good reservoir. They have porosity of the carbonate, and they have some of the permeability between the rock here. So the source rock we start to have the oil or gas migrating to top, and it will stuck here because all this area above is all we call it cap rock. It's a very they call it low permeability. So the most of the hydrocarbon will trap within this carbonate spike or hill or spike. So this is the more one of the popular features of Sarawak. Okay, for static modeling workflow, we have the input data from the logs, from all the mappings by the Petrel from the GNG study, and then you have the structure being mapped by all this simulation. We have all the 3Ds, and we have the layers identified by the features from the seismic as well as from the well information, that we can fine tune. And finally, we will trace your reservoir with the different colors. And of course, when we have that, we have to do the property modeling to decide on the volume of the hydrocarbon, the movement of the carbon that is possible, and what is going to be other issues like recovery factor will be among the factors to be to be decided or to be determined by the property modeling. Okay. And then finally, of course, we're talking about the volume, which is the important factor because when we explore oil and gas, volume is very important features that we have to decide because it will decide on the revenue of the project, how much oil or gas that are going to recover, and of course, the how long it can last. So it become the economics of the project. Okay. So once we have all this done by the geophysicists, the geologists will start to come in, try to see the answering about the field itself, with all the samples. We try to talk about the petroleum geology that will go through all the expectation and of all the origin of the oil, the positional environment, and so on. The positional system we call it. And then according to another mapping, geologists will do another mapping that will involve more of the property, the volume, and so on. And of course, they try to correlate information to have the better result. Okay, so when we talk about all this study here, generally, the construction of stratigraphy will help everyone to understand how the field will looks like and what is going to be the potential of remaining hydrocarbon that can be also be within the area. And of course, they want to really describe their stratigraphy so that when they explain about the volume or the potential reserve of the area, can explain much more conveniently, much more confidently. Okay, so in terms of the study about geologists, they start to go through all the fault system, try to understand whether the fault is going to be like a macro fault or major fault, and whether the fault is sealing or not sealing. All that by understanding the features, we call it the nature of the positional environment of the area. Okay. And then, of course, when they have done that, this is the typical structural map that they will draw. you can see that geologists will have the information there. Like I say the same thing, the XY axis on the top is much more stretched, more on the high volume, a high scale, but the depth is small. So if you stretch the top scale of this map, you can see that it come almost like a flat, more like a flat features rather than because this is much more because of the scale issue. But just to show you that actually there is a depth difference from one point to another, but it's going over long distance. So of course, for geologists, they try to identify all the potential fault based on the seismic. And then from this fault, they try to see whether one of the reservoir will be isolated from another, or they still continue to be connected to one if it is a non-sealing fault. So all this volume will be based on fault because by failure to identify fault, it gives you a false understanding about the volume, the RV, because we call it we call it the volume itself. Okay, so the same thing happened to another side, is southwest to northeast, and it's northeast because just a cross section of the review. So once you combine the 2D and 2D, it becomes a 3D more or less in terms of the features. You can see how the formation is gradually going up, and the potential fault may be reviewed on another side of of the cross section. Okay. So that's about the geological part. So now we go for reservoir engineering. For reservoir engineering, you can see that we're going to go more or less on the dynamic modeling. So we ask just the basic understanding about static modeling and dynamic modeling. Static means that when it is in the original condition, nothing move. For example, all the accumulation have been happening about hundreds of millions of years ago. So there's not much movement. So they're going to be static condition studied in that model. So we're talking about the original condition. But when we talk about dynamic modeling, it's talking about what if we start to extract oil, what will happen to the oil movement? What will happen to the pressure declining? Or what happened to the movement of water or gas within the reservoir? So that's why dynamic modeling is actually being covered much more detail and is a true computation of the potential of the reserve. Some static model have shown a good volume, but when you go to dynamic evaluation, dynamic simulation, you see that they have issues with permeability, issues with the sealing, the fault itself, and so on. So you have to really understand this, what we call it, dynamic modeling. Okay, for reservoir work, in general, they're going to go for pressure analysis, temperature analysis. Of course, this will help to decide on the we call it the dynamic situation of the field when you start to produce. The fluid properties, of course, you decide oil, gas, or water, and the influence of what you call the contamination, if there any CO2 or H2S in the oil or gas. And rock properties, of course, they will cover the rock strength through the core and the sidewall core. And we have to understand about the structure of the rock is going to be like having a cemented rock or going to be like affected by some other debris or fines within the rock. And of course, the SC analysis is going to test each reservoir in terms of producing. It gives us a better idea about permeability and porosity of each reservoir. So this is the situation of the requirement by reservoir engineer. So all this information will be going through for static modeling. Upscaling means that reservoir engineer will revise the static modeling, putting it in a much bigger scale, and then of course it's going to go for a much faster simulation process. Dynamic model, and then of course they have to go through all the uncertainties when they evaluate through the reservoir dynamic modeling. At the same time, you're going to see all this reservoir management plan coming in. So this is typical, we call it the cell, or when we do the simulation, we can see that for cell dimension, normally for static modeling, they go for 100 meter and 100 meter by 1 meter. So one cell is 100 meter to 100 meters. So if you're going to have, for example, 20 kilometers by 50 kilometers of field, then it become million. So for example, this particular field here, we have upscale, you're using 2 to 3 meter rather than 1 meter. So it's going to be much smaller size. So in terms of the cell, for static modeling, about 4 million cell, but for upscaling, about 1 million cell only. But this requirement is because we want to do repeatedly multiple simulation process. So it's going to be, for example, one process before it takes about 1 week sometime, and it go down to 1 day. But currently, we can make it a process of one cycle within 5 to 10 minutes because of the computing power that currently available. So the processing now become better, so it helps a lot. Okay, so of course, when you go to static modeling, you can see also you have the different zone. For example, in this particular case, you have 7 zone. And of course, static modeling, they have all those numbers here, and then you can be reduced. For example, the number of layers is reduced in your upscaling modeling because we're going to go for multiple simulation. Because for static modeling, they go only one or two, three simulation, then they conclude. But for upscaling, reservoir engineer, we do a repeated process of reservoir simulation. Okay. Now for the, just go briefly on the understanding about the modeling. So you can see for reservoir model, they need a feasibility report, which is coming from lab. Reservoir then they start to really do compute because it's going to be dynamic. What happened? What if we start to produce 1 year, 5 years, 10 years, 50 years? The depletion will come in. We want to see the depletion. So if we want to see that, see how many platforms that we need to put in the drainage. So depletion will be much more if it is more well drilled, and then it is going to be less depletion if it less well drilled over a period of time. So and then at the same time, depletion can be controlled by whether you drill horizontal well or multilateral well or vertical well or slanted well, different. So EOR, enhanced oil recovery, also be part of the plan. If you see all the scenario here, whether you need enhanced oil recovery to be able to help you to to improve the recovery of the field, recovery factor. Okay, so we're talking about the well construction itself. Well construction, once we know all this, then we know that how many well to be drilled and how we do have to complete the well. Normally, if you go to smart completion, then of course you optimize the production, but you have to spend more money on the smart completion or intelligent completion. But it will be more or less of the cost benefit analysis to be done on that. Okay. Okay, now we go to the next one is reservoir management. Okay. F. SWC, water content. Saturated water content. SWC is called sat wall core. Sat wall core is actually a core that being covered. And what happened when we drill a well? So when the well is still in open hole, we can take a sample of rock by running in the wireline lock, and then there's a gun process that explode. For example, we have a space out the subwall core. We just the gun will explode, and then there'll be a cone going through the formation, and it'll be pulled back to the wireline process and pulled out to surface. So this is the sidewall core will be used for analysis of the rock. Because if you're talking about running a separate drilling assembly with the core barrel, and then you're going to core. It's going to be very expensive and very risky. And then sometimes you get stuck and so on. So that's why the sidewall core is an option, but the quality is not good as the real core. So anyhow, you have to bear with that, with that difficulties and so on. Okay, sidewall core. So proceed. Anything more? Any more study question? No. Okay. Now for uncertainty, this is another area where we need experience. We need understanding about regional area. So we talk about uncertainty. This is where you're going to understand what is going to be our issue here. For example, you expected the reservoir quality in terms of porosity have a big range, and then your permeability might be another range. And in terms of the fault, sealing or not sealing, all this uncertainty must be considered to be able to conclude your reserve potential. Of course, this is a reservoir surveillance plan, or we call it reservoir management, RMP, the same concept. So this is the plan that we start to be used from day one, because we recover information about behavior of the wells, and then from the construction, from the production of each point of the reservoir, we can see that which one is producing as per our simulation, which one is not. Then we try to understand what's the reason behind of each variation, and you make all your potential mitigation plan. So of course, the last one will always be recovery factor, because some field is very big field, but because of the position of your wells, because of the extension of of the reservoir, you cannot drill too many wells, because of course many wells means that you can recover more. For example, recovery factor for that field, for example, you need to drill 6 wells to be able to get 50% gas. But if you drill 3 wells, of course you're going to have about 20% recovery factor. So it depends on number of wells. But the problem is that wells is very expensive. So you drill more wells, the more you're going to spend on your capex, your expenditure, capital expenditure. So less profit you'll be. So you try to find a number, a border where it's going to be the optimum number. So it's under the well count that we're going to discuss later on. Okay, so this is the Masato reservoir simulation. This is one cube. You're talking about one cube, which is 100 meter, 100 meter, and 1 meter, for example. So each cube. So you put all the each cube in your model, in your reservoir, it's going to be like 4 million, for example, for your static modeling is about 4 million of cubes, and each cube has its own properties. Yeah, pressure, temperature, compressibility, and so on. And then, for example, this is for of course they compute the volume of the reservoir on this cube here we reduce from 100 meter 100 meter to, let's say, 3 meter or 2 meters. So it's slightly a bigger size. So it's going to be about 1 million, for example, of cell, and that 1 million of cell we put in the simulation, and we try to, for example, try to say that okay, we have 5 wells. So when 5 wells be produced, what will happen after 5 years, 10 years, 15 years? So all this simulation using all these cubes, we give you a much more better representation of the actual production before you produce, so you understand the challenges. Okay, so at the same time, according to static, this modeling here, you can see all the numbering that we discussed before. We have the number of cubes and so on. Okay, so all the parameters that we shown here. This is a typical data that you can see from this dynamic modeling, that we use for computation. So comparison, this is quite important, and this is quite unique area. I think what happened is that when I go through a situation of the comparison, static modeling versus dynamic modeling, you can see that most cases, if it is good references with the field, for example, this field have very good references surrounding, so you have all the offset field that give you some help. So when you do static modeling, we can see that the result is what for this gas field, gas initially in place. So for you can see for this static modeling, they are expecting all these 9 zones here. We go to about 9.9 trillion cubic feet of the reserve, 9.9 trillion. Dynamic modeling is showing that 9.8. So the difference is only 0.56%. For me, normally you can see the difference up to 4-5%, or even close to 10%. But because of the area is very close to the nearby field, so they have more information, more data, and of course with the good reservoir simulation that we have now, all these numbers become very close to one another. So it's showing the accuracy of the prediction, and that can be a good use for us to do our economic study, dynamic analysis based on the volume. Okay, but there's no recovery factor yet here. It's only the volume, no recovery factor. Okay, so in terms of we call it the uncertainty. Normally, what are the subject to discuss on uncertainty? Also, always this a few subject here. It's talking about permeability, aquifer size, rock compressibility. All the uncertainty, the ranges, will decide on the reserve or the productivity of the field. All this is actually the list of uncertainty on the reservoir. Okay. And of course, the same thing happen, like you go for what is negative impact, positive impact. So all uncertainty normally you can map out with all the parameters here. So this is normally presented in this particular case. You have all those sensitivity that happen here. So what if going down? So this is actually the plateau years. For example, the plateau years here is about, let's say, 15 years. What if the probability is for example is less by 6%? So you can see that your plateau did reduce by 10%. If your probability is more by 4%, then you can see that you go almost like 7-8% more on your plateau days. So the extension of the plateau days for production is more. So that's more or less the understanding about the all this impact of your uncertainty, the high impact, moderate impact, and low impact based on the you can the chart that you see here or the variance here. Some is very marginal, but the big impact is coming from probability and fault, as well as the this is probability, the skin or the damage. Okay. At the same time, we're talking about how we decide the number of wells. So number of wells, normally you can see, we get to define the field geologies or the target and the capex, OPEX, or the budget. Because the more wells, the more you're going to spend. And then with this information reservoir data, you will decide what is the best to put in well location, your target location, and then how much you're going to recover from each spot. So for example, you have 9 trillion of centimeter cubic feet of gas, but if you space about six wells, for example, then you have to cover about 50%. If you put it 10, you have to recover about 70%. So it's all a discussion about what are the economics of doing that, because the well is expensive. One well could be a range of about, let's say, 30-40 million. And then, if you drill 10 wells, it could be 400 million. So the project is about, let's say, 2 billion. So it's about 25-30% of the well cost contributing to the project cost. So it's very sensitive to decide the number of wells. So it's the claiming curve analysis that normally be popular to decide the number of wells. And then, of course, we run simulation to see the spacing and, of course, the production profile of each field. And then the economic evaluation, and we finalize the development plan. So this is the process on our wells. So example of the analysis done. So the tubing head pressure will be about 14-15 psi, and then the tubing size 7 inch. We show the plateau days for 5 wells, 12 years, and then for 6 wells, 14 years, 8 wells, and so on. And then you reserve that you're going to recover normally is about because from 9 million, remember you have 9 trillion, now you have 6 trillion, so it's about 60% recovery factor. So PSC life. So you must understand the difference between PSC life and the field life. For example, PSC life is that the production agreement is about 25 years. So we compute based on 25 years using simulation, see how much our recovery factor. And if the field extended, for example, the field life, for example, can go to 35 years. The 35 years, based on the study simulation, is about 60% you can recover at the end. But normally we concentrate on the PSC life because our economics will be based on the PSC life. And when we see all this, all this number here, we decide which one is the best. So we can see that the deviation start to be very marginal at the end. So 6 well it seems to be the right number of well to recover 60% of the reserve of 9 trillion. Okay. So this is the assumption. So one well is about 900 million. Okay. Okay, what else? Then, of course, one well can go to potential of 7 inch can go to 190 million scale or even 200 in some cases. And of course, our reservoir pressure is about almost 6,000 psi. So you can see the range that the pressure is so strong that it can still, produce through quite to the field life, covering up to for 14 years plateau days, and it can go another 11 years to end the PSC lah. Okay. Okay, so I think the next one is to go through. Let me I just try to move my chart. Is to go through the diamond well. Once you decided on the reservoir, the reservoir simulation, we decide, okay, this is the particular spot, the best spot or the hot spot that you put in your 6 well that will produce the 60% recovery factor. Okay. And then, of course, we're going to have those information like what are the factors that if you have compression or without compression. That means that if you try to, for example, lower down your wellhead pressure, and then you're going to have more. So without compression, it's going to be higher. Compression means that you sometimes talking about allowing the well to flow more. So the effect is always more gas or less gas. But of course, the impact of something like the production profile decline very fast or not, it depends on whether you're going to have a compression to allow the gas flow to the surface very high. For example, you can see that we talk about 1400 psi. You remember the 40,000 1450 psi? Actually, we can reduce it lower down to have a more volume. But the problem is that the pipeline also needs some pressure or the processing process. So when we go through the separator and so on, we should be able to maintain about, I say, 1000 psi before we pump it to the pipeline. So we need still some strength. So this pressure here need to be more or less to a certain limit that you cannot change. You cannot go too low, otherwise you are not able to pump, or you have to need a bigger compression facilities to pump the gas through the pipeline. Okay. So once you have to done that, of course, we're talking about the agreement based on the study here. We're talking about 6 wells. And then we're talking about the compression requirement. It shall be further studied because, like I mentioned, if you know that you need 1400 psi to be able to pump through your pipeline, if you want to lower down, then you have to think about some other mechanical process for pumping through, which is cost money, capex. So you have to decide on the economics for having that compression. So without compression, it always be our basis of design, basis of calculation. So based on that, if you go for, let's say, for low pressure compression, you can improve. You can go lower down, you can improve your recovery. But of course, like I mentioned, it depends on whether you are allowed to do that because of the requirement to compress through the pipeline and to export the gas to onshore or maybe to some other area lah. So without pumping, this is only going to be your recovery factor about 56%, not 60% lah. But if you have that, it's still 1%. Okay. So now it's going to be a production profile. So since we have enough time, so maybe a few questions before we stop for a break. I mean, any more question that I can more or less attend. Otherwise, we can stop for a while and then we continue about 5-10 minutes. Okay. Any question?
Hi, Abdul Kahar. Yes, the slide will be shared. Once everyone have key in the attendance and feedback form that I will be sharing now. Give me one moment to share it. So yeah. So for those completed this form, I will send the slides by the end of the day. Okay. So if you have any questions if you don't have any questions, so we'll be back in 5 minutes. So 11:03, we'll continue the session. Please take a time to fill in the feedback and attendance form, yeah? Okay. While we have a rest for a bit, I think Patik can answer a few questions here. So Fatini asked about how long the people at the platform need to stay until the project ends.
Okay, the question is more about like, when we do a project.
Patik, unmute.
Dia tekan tak mau. Yeah. Okay, the question about how long people stay on the site. Because actually the project, for example, when we install the platform, the crane bash, and we'll try to pick up those platform on bash, open bash. So the process takes, for example, building up platform can be almost like a 2 months duration, where they go put a survey and then have the location identified, and then they pull everything on location. The crane bus start to do the preparation for picking up the platform in stages. So it had the bottom part of the structure, and then of course the top side will come in. So the bottom part might take about 1 month, and then they wait for the top side to come in, and then they put in the facilities on top of the structure at the bottom. So all those takes about 3 months for installation. But of course, this is where people will be working there almost non-stop, 24/7. Even they work, whether they're going to be bad weather, if the weather still allow them to do the work, they will continue. So 3 months normally for foreign workers, they go and stay for foreign expat and so on. I think they're going to go there for about 4 weeks, and then they have a rotation of 4 weeks on and 4 weeks off for the expat. But normally for supervisor, since they are worried about the continuous monitoring of the project, sometimes the supervisors and the leaders, mostly the project management, they will stay there, and so we stay there about all the 3 months, and they will get off maybe once a while, like for example 2 or 3 days off when there's some period of for them to be allowed to go back to town to do some preparation of or maybe of the issues or planning for the next job and so on. So big boss they will only stay there, but for other aspect they go for 4 weeks rotation because they have replacement. So they have, for example, all the crane operators they go for 4 weeks, and then they will have a change. One shift is about two shifts, so we have two shifts, 12 hours each. So they have rotation like one person will be going off and then replace with another one, another one will go off. So they will have overlap, a good overlap to make sure continuity of the understanding of the difficulties or complexity of the project. So 4 weeks on, 4 weeks off, and then sometime for the big boss they will stay longer on board. Thank you. Any more?
Okay, I think there's a few questions. Okay, untuk Pak Tip dah tak ada lah. Okay, so I'm addressing a few questions from the chat box here for the admin. So basically, Ramachandran asked about the attended course for last week. For those that filled out the feedback form, I've already shared the slides. If you guys haven't, okay, for today's feedback form, perhaps you just note that can I have the slides from last week's too? So I could just include you and then the last week's slides too.
Hi, Ivy.
Okay,
Uh,
can we continue?
Okay.
Okay, Ramachandran, I will be sending the notes later after the class ends definitely. Okay, I think Pak Tik can continue the session.
How industry adapting to energy transition, Shukri. Nak jawab dulu tak jawab?
Boleh lagi. Dia nak jawab dulu.
Okay. Jawab? Okay. Ni I think there's a question about how the industry adjusting. Macam mana soalan dia?
How industry adapting to energy transition?
Yeah. Okay, now I think there will be a lot of discussion about the renewable energy coming up. And of course, people also talking about hydrogen in our system here, replacing the oil and gas. But what happened actually, the oil and gas have been in the system, in our energy system for hundreds of years. And then it become more matured, much more comfortable, much more stable. And then even we can see that whatever the changes to the renewable energy seems to be have their own target or their own customers, but majority of the customers in the world still looking for, we call it from the from the normal oil and gas, fuel oil, fuel energy. And then of course you can see that even the fuel energy is actually the easiest way to process, in a much more convenient to in terms of the supply chain management, SCM, logistic wise. You can see that to do the drilling a well, it becomes standard nowadays. We can see that we can have recovered a lot of oil from different part of the world, even in Arctic nowadays, in deep water, in very deep formation. All that become a requirement for recovery of oil, and then the demand still high because of the industry in most part of the world, which is not on the, we call it the more, we call them the big players. They try to avoid having oil, and then they try to shift to gas. But it looks like the nature is following that style, because there's less oil but more gas coming up in the market. You can see that discovery of gas is huge in the world, especially in Malaysia. We discover more and more gas, and the oil is become less and less declining in terms of production. But we are lucky for Malaysia to have more gas. We export more gas to the world, and then of course in other part of the world they also discover most gas field. So the moment we have gas, the issue of pollution is getting less, but still we're talking about much more convenient in terms of the supply chain to be able to still maintain the fuel energy as part of the for a year to come. I've seen the renewable energies have their own customers because the demand of energy is more, but still the remaining part of the requirement for energy is still captured by the fuel oil or fuel gas. Thank you. Okay, so now let me share with my think to be eligible. Okay, so I think there's the one question asked about what experience or what knowledge you have. Hmm. Okay, so I think we'll go through. We try to answer that question later on. So module 4 is production technology. As you know that once we come up with all the studies evaluation, and we start to to understand that it's economics to produce from this field, then we go on the study and come up with good economics. So we start to do the production technology. So what are the areas that cover the production technology? So it will cover the flow insurance, assurance, the driving mechanism, the drainage point. If you go, you can see that it is already covered by reservoir, but for production technology, they go even detail. Because what happened, reservoir does not include the mechanics of production. For example, in drainage point itself, you're going to have what the size of the hole that we're going to extract from each point. Is it going to be a 6-inch hole? Is it going to be like 8.5-inch hole, open hole, to be able to produce? And then each one have their own skill, the wellbore skin, and then after the reservoir skin, and a perforation skin. All this skin actually being covered by production technology to understand the resistance to flow that coming in. Then also they're going to have for example, all the production index going to be how many barrel of oil per PSI drop, or how many million cubic foot of gas per PSI drop. All this will help them to identify the ranges, in terms of the pressure drop over that particular well. Depletion strategy much more detailed under production technology, because they're talking about each point. Because if you talk about in general, they have to understand about each point. This is different and much more focused. So this is the role of production technology to be focused on what actually the real production capability of each well. So for this case, for example, the proposal given to them is with six producer based on reservoir simulation, and each well demand about 900 million scf so that they were able to produce, for example, about 1 trillion of gas per day from this field. It's a huge field. So like as I mentioned, the reserve is 9 trillion, recoverable is about 6 trillion. So over maybe 35 years, okay, or even more. So a 7-inch tubing can deliver more than 150. According to the analysis of the PTEC, it can go to almost 200 million scf per day. And 6 million, that one well completed in open hole. So talking about open hole completion, and they need the tubing that go through on the CRA. Permanent dial gauges is to help the reservoir management to monitor the production because they need to capture the real pressure at the bottom, real pressure and temperature. So this gauge will tell them, because once you have the surface without this gauge, reading at surface will give you some error. Some error is quite big to be able to understand the real behavior of the reservoir, based on the real NC2 situation. Okay. And then, of course, I mentioned before, for PTEC, we try to use all the DST result from the previous exploration and appraisal well. And with this operation result, they can actually plot what they call it. This is inflow performance, review for the well. So based on the DST, they can, of course, also draw this more or less this graph here, inflow performance. And then they put in the 7-inch resistance and so on to they can see that this field can grow almost like 200 million scf to be able to flow to the optimum with the resistance from the rock and so on, inflow from the ST result. So this is more or less the understanding that the capability of 7-inch will have up to almost like 200 million scf per day for this one well. So you want to use 1 million, you need 5 wells. So 6 wells means that one continuing, six producing, one on standby. Yeah. So they also use to calculate the erosional velocity. Then they can see that when you produce the well like gas rate on higher rate, then your friction will be much more. So because friction will cause damage to the tubing, so there is a limit. Like for example, they try to make sure that when you have the pressure, the reservoir pressure pushing about 200, then this is going to be your flow rate about 200, which is around this area, 200, and then you're still within below the erosion rate. So 200, which is 200 here, and then you have your erosion rate, which is this number, which is lower than this one number. So it's within range. So you're going to have a very minimum erosion situation of the flow to your tubing. This is typically the graph here, and then you have the improved performance flow, and then you have the potential, you have original flow, all this adjustment. But this is morely the conclusion from the study of the field, from the ST result and from the friction of the 7-inch tubing, and that's the production capability. Okay, tubing sizing also same thing. Like they check through a few sizes, and finally they found out the 7-inch is going to be the best because it can meet the 900 million scf requirement. For 6 wells, we are able to produce that. So they meet the requirement of 6 million. Of course, once the well depleted, the 900 million after 14 years will go to 800, 700, after the 25 years. And then, of course, it's going to be less, but still within the range of our economic analysis, even though the declining is being expected. Okay, so this is more or less the understanding about the tubing material. Of course, we have all the pressure, temperature, the amount of CO2, the partial pressure, and the H2S ppm as the partial pressure from the H2S. So the partial pressure is going to be used, in our determination of the tubing material. So this is what we call it the selection table from Sumitomo. So we're going to have, for example, price is going to be the starting from CO2. If it's less than the partial pressure is less than 2.9, no, it's there you go for a carbon steel. But the moment it go more than 2.9 psi, for this area is more, for this field is more, so they go to the next step. So temperature. So it is more than 1.45 kPa, and then the temperature is affecting the salation. If it is if less than 1.5 psi partial pressure, this is the pressure, the temperature will decide on the material. So this is how we read it. If less than 3 kilopascal or certain psi, I can't remember. Okay, never mind. We will convert later on. So this temperature, each temperature we decide on the material. So what happened actually, you can see temperature effect on the selection of the material. As we go lower, then the amount of nickel, which is very expensive material, is going to be less. So the lower temperature is less. So mostly we put it at the deeper zone, we have the high material. At the upper zone, upper completion, we have a slightly lower content of moly. So the nickel is very expensive. So the next step is always this. Duplex is unreasonable, but the moment you go to nickel, it's going to be very expensive string. So this is more or less the situation of temperature. You can see the same thing. As temperature going down, you can see that you can less amount of chrome, and so on. So normally the popular size that we're talking about is 17. This is the in Malaysia, we always this situation of less than 3 kilopascal or maybe 1 point, I think it's 1.45. So the temperature is 200, super 1317 chrome. It's less than 160 degrees Celsius, then super 13% chrome. So the section here. So another way is actually talking about the situation, the flow process of another style. So this was starting here, then we have carbon steel, and then we have corrosion, and this is a map to be used, which is the one. This is the map. And then all this process of understanding the between the CO2, the pH condition of the water, plus the H2S. So all this process also help to decide the material. Okay. Corporation design, as you know, we're going to produce to prepare a corporation design for the well. So this is how we're going to go for example, this well we drill up to 8.5 inch hole at the last of across the reservoir, and then we to run the completion. So this is going to be 8.5 inch hole, and then this is the 8 inch perforated liner, So it's open hole completion. And you can see that this is the 7 inch casing, which is 70% chrome because of the chart shown here. And this is the connection, WM21. It's a gas tight formation, and it will be more or less installed. At the top here, you can see that the 958 inch here is going to be like T85, which is the quite high strong material. And it is isolated by packer, so this is going not to be exposed with all the corrosion, so they can have a slightly normal metal, but it's going to be high pressure, high material, okay, material for the casing, for the tubing, sorry, for the tubing to be run. So they have 958 inch casing here, and then they have the 10 3/4, the 10 3/8, and 30 inch. This is the casing redesigned by drilling, and tubing is required by PTEC. So the way we design is we have the sizing, then we work upwards. 7 inch need 958, then 958 can fit 10 3/4 and so on. Okay. So module for number 5, the Oman option. The Oman option is where we start to develop the field, and you can see that for the field development concept, the field have all the wellhead. So this field A that we're talking about now, we have a CPP, Central Processing Platform, and then all the future will, because according this is all managed by Petronas, so Petronas understand that there will be another field coming up around the area, So if let's say example, then what you do actually, you're going to have a riser platform in between. The riser platform is a transit platform where all the hydrocarbon from each field, for example, from this field, you go to our CPP, you go to the riser platform, and then so all other field in the future, we also tie into the riser platform. So the riser platform is being prepared to accept maybe another 4 new field in the future. And then, of course, we have one riser platform, we have the onshore facilities. So all the piping, the oil pipeline, the gas pipeline, we go into, this is going to Bintulu, or the gas plant, the train. And then, of course, if there's any refinery, like for example, in Miri, then they will go through a separate pipeline to the oil refinery, Miri, Labuan, or KK, and so on, Kota Kinabalu. Okay, then, of course, the element concept. For the element concept, you can see that we have the base case, for example, in this field, They might have, this is, for example, this one field, this is not relevant to that field. For example, one field, they have, of course, one platform here. This is like in the pipeline going through this is the FPSO, 700 barrel. And then the tanker will come in and out to drain the content here. So you can have continuous production of 700 barrel. The tanker might be coming up and loading, each loading sometimes for 500,000 barrel. Sometimes each package is about 400,000 barrels. So it depends on the size of the tanker to drain through the FPSO, floating storage and offloading vessel. Okay. And then, of course, the option one, sometimes you evaluate what is option one. Option one, actually, rather than having through the FSO, we take up FSO, we have the direct pipeline from this field to the nearby platform. So we actually ride on to the nearby platform. So the nearby platform is like a riser platform or some other field. Then you're going to go to shore. So we make use of the existing platform. For example, the platform is been designed for, say, for 60,000 barrel, but after 6 years, it's going to be down to like 50,000 barrel. So there's about maybe 10 or 15,000 barrel available. So is it enough for you to ride on based on the capacity or of the design of this platform and the pipeline size? So this is option one. Option two, actually, you try to go and have your processing on the floating storage. So what happened? This is only for storing. You have the processing here. This is for storing, floating storage. But here is floating, processing, and storage and offloading. So other than having FSO, you have a FSO here, which also process. You don't need a platform anymore. So you have, but for this you need a subsea well completion. We have all the wells in subsea, and it all tie in with the umbilical, the pipeline, with the control going to the floating platform, and of course we produce. In this case, you can see that you remove the requirement of platform and make the project much more lower cost, but we have to spend more on your floating storage because you have processing there. And of course, the tanker will come in and out to offload from the volume over here. So this is the option that I think that being intended produced by one of our new player in Malaysia to try to use FPSO with their marginal field to really reduce the cost. So it's interesting to see how much it will cost or economic analysis that they have done, whether what they thought is going to be a reality lah. Okay. So for field development plan, you can see this is the concept. Only the in general, you have the processing platform, then you have all your wellhead platform to drill, then you have all this pipeline link. So you can see that this is all this particular wellhead, and then you have your tanker over here, link. So you don't have to have your pipeline to the shore. So what is the decision for pipeline? If it is going to be a very far, for example, 200 kilometers from this platform to shore, then the cost of pipeline is so expensive. So it's always be cheaper to have the floating storage rather than having a pipeline. But which is close to shore, then the cost of pipeline is much lower. So it's always better to have a pipeline to shore and not using FSO. So it's always based on economics, whether you are far away from shore or you are going close to the shore, and the study of cost benefit will be done on that. And of the sizing of the pipeline going to the shore, to the loading here, it depends on the size. And you can see all the pipeline coming in. So all these pipelines have oil pipeline, we have gas line pipeline, and the water injection pipeline. So all this platform here have this 6 oil producer and 2 water injector, and this 8 oil producer, 4 water injectors. You can see drill platform here will have a few wells to be able to have oil producer and water injector. Sometimes they are drilled together. Sometimes water injector is drilled later on because, like I mentioned to you, some field have a good water drive. Then they produce the well naturally, and then maybe after 5 years they start to plan for the water injector, or sometimes they have the water injector ready to go, and then observe the reservoir performance and activate the water injection. But water injection needs another facilities on board to be able to inject the water, and then all the processing of water quality and so on. So everything costs some additional capex or opex lah. So that's why to decide on the water injection, we be going through the simulation and then we go to the economics analysis and decide which way to go. Okay. So if you see that from this, we have about 24 oil producer, example, they have about 3,000 barrel per day. So we're going to have about 72,000 barrel a day for production. Okay. So if to 7,000 thousand barrel per day, if the holding period for 15 days before the offloading from the tanker, the FSO must be designed for 1 million barrel capacity. So this is how it depends on how comfortable they are with the tanker coming in place, because there will be a special marketing department that will decide on the selling of the oil so from various customers or client. So they will arrange so that every 5 days there will be a tanker coming in, or every 5 days, so they always be draining the capacity so that platform can continuously flow, non-stop, the full capacity of the 70,000 barrel a day from this platform to the FPSO for storage, and then drain or being exported to each tanker that come in. So you see this concept of field development plan. It can be different concept. It can be this typical concept lah. Okay. So for water injector, for example, we have 10 water injector. If we plan to pump 7,000 barrel, because with 70,000 barrel that we produce, we pump in 70,000 barrel back, more or less. So about 10,000 barrel, 7,000 barrel per day. The facility should be able design to inject about 10,000 barrel, so there's some allowance for that. So this is for example, a field in Sabah Sarawak. So this is our field, for example. Then this field is very close to the nearby field. So of course we have to decide whether we have to tie into this platform, or we can go straight away with our dedicated line to shore. So it depends on the economic analysis. So in this case, I think the study showed that we have to have our own. For this is a gas field. So gas field, then it's going to be a dedicated pipeline because a huge quantity. Then it's going to be the pipeline, because no other field in here can accommodate such huge amount of for gas, for example. Okay. So of course, when we talk about drilling, multiple wells in one platform, some platform have 14, but in this case, you have more than I think about almost like 30 wells, 20 wells, 30 wells. This is my project with Talisman. We have the Bunga Kekwa A, we have B, so this I think is A. To go and penetrate, because our design for Talisman is we call it monobore plan. So monobore plan is that we try to target one well with one well. So that's why we have more, but it can produce you much more better recovery. At the same time, it can drain to the maximum production per day from this platform. These are typical slot each well, and one well go to different direction, meeting their target. Okay. And in terms of 3D, this is Talisman project, where one platform about 25, 30 wells. You can see that some wells have been drilled to certain location. And then afterward, we come in and then we drill more wells inside to drill more platform. You can see that even one field can have about 50 wells, even 60 wells of different depth, because they go for different layers. Okay. So how to estimate the drilling and completion time? Because you can see that, a 6-well plan, for example, then talking about what are the issues based on the experience of drilling of the exploration well, the appraisal well, the exploration well. We know what the issues, and then we have sometimes we have the gas, shallow gas. We have pore pressure issues. We have H2S and CO2. And of course, when we list down, we can see that based on the experience that we have with offset well data and the current well data that we have within the field. So we have about all these numbers of this. Drilling this 49, for example, completion is about this. This is going to be deep. This is a different example of I think deep water. I mean deep well, HPHT. So you have about 400 days. So you're going to be more than 1 year to drill. So sometimes you want to make it fast. They have 2 rigs, but because it's only 6 well, then it's one rig going to be like, for example, one platform. And this is one platform. So this is gas field, sorry. It's about 400 days. It's going to be about 1 year. So plus the rig move, rig down is 471 days. Okay, this is on the timing for the well. And then for cost. So for cost, we're talking about rig rate of 135,000 per day. And then the tangible cost tubular is per the contract and other costs. And you can see that from this analysis here, we come up with the cost of the well based on the days that we agreed. And of course, the cost will be about 396 if we include the rig move and rig down. It's about close to 400 million US dollar. So that's the okay. So when we talk about all these numbers, we're talking about maybe having the opportunity to explore. We call it all the optimization that we have done. So we try to see how we could manage the third party contractors better, so that they perform well, less problem. And we do geomechanic study before we drill, so that we must understand we drill additional well, there'll be another additional issues of hole stability. And then after optimization study will be done, and then batch reading, batch completion is going to help us to reduce the well days. Logistic control, saving logistic, sharing all the supply base, sharing some of the, we call it the storage capacity and so on. Offline activities is where we can try to do two jobs at one time or three jobs at one time. So normally the rig have to be prepared to be able to do offline, so that we can reduce the drilling days for each well. Okay. So this is the area where we talk about abandonment and decommissioning philosophy. Because once we come to the end of the field life, where the production is too low to really balance up our operating costs. So this time to really decided to end our project life, and then we have to really abandon all the wells, and decommissioning means that we cutting off all the platform structure, cut off all the pipelines, make it clean seabed again, and then we declare to the host government, like Petronas, saying that we have done a proper well abandonment as well as the commissioning. So you'll be surprised, what happened actually the work here, but on abandonment is going to be quite reasonable, not so much like but in terms of the removal plan for the decom, this is abandonment expenditure. Removing the platform including commission can be almost like 200 to 300 million. It's going to be very expensive for decommissioning. Abandonment will be about 65 million. This is abandonment cost only. But for airbags, you can see that the number is huge. So if the project is about 2 billion, so you're talking about 10% or about 20%, close to is on the commissioning cost. So normally your profit will be drained out once you need to spend more money. So that's why the economic is important. I just understand whether you're still profitable at the end of field life, because you are committed to spend about 300 million, just to abandon the field. But in some PSC, most of the effects is covered by the host government, because they get a lot of profit from our project, and they should be able, to accommodate this. But what happens sometimes they want to make sure they are not having such impact. Just like operator, they ask you to pay slowly through the barrel. For example, each barrel you must contribute $5 or $2. So hopefully by that contribution, Petronas will accumulate enough fund to be able to do the project end. So there's a few style of how to manage the ABEX, the abandonment expenditure or the commissioning of the field. So abandonment cost about 65 million for 6 well, because it's only 6 well, easy. And then of course front end is the building up the facilities. Is how they're going to, because facility will cover building up the central platform, all the wellhead platforms, the pipeline. FPSO normally is rented, it's going to be by third party, so it's not much an issue lah. So for facilities engineering, normally this is done by special group. We're talking about the engineers, mechanical, civil, electrical, all those kind of people that all the machineries, rotating machineries and so on. So laid out plan, they don't try to make sure that they have a plan where they can optimize the production. They allow some room for expansion, and that's some space. Because if there's too much space allowed, of course it's going to be very expensive. So the bigger the platform, the more capex, the more money you have to spend. So they have to think about all the best design, and with the knowledge of think about 100 years for the design of the field. Most company, the design company, actually like facility design, FED company, they are very smart. They have special software, and they have expertise to really coming up with a good plan for your project. Okay, it covers some on instrumentation. Environment is very important. So even when we design, they always make sure that they have the capability to manage zero disposal, so that no all or any any contaminants from the processing itself will not go to the sea. They will be collected properly and disposed properly. And the hazard studies is understanding about the or the area. Some airfield within the marine transportation, the cargo or the ship line, so they have to be careful about that. Some of the areas too far, or in case of bad weather, they might be able to be stranded for about one month. So how they're going to handle the human there to be surviving for 1 month, for example, then? Okay, project economics also will cover all this indication, and to make sure that they have enough profit, because as you know that we will talk about project economics, we're talking about PSC agreement. So PSC agreement saying that okay, if you're a guest, you're going to be like 60% to the government and 40% to you. But with this oil, 70% to government and 30% to you. So we have to really come up with the understanding that how much revenue or project profit that you might be expected from the field. Okay, so project management from is quite important. And once we go to the project, it's going to be a very detailed understanding about the management itself. They go into detail about the scope of management, define. So this is very professional job, and you have opportunity to really join this front end engineering. You will learn a very detailed management of technical engineering, safety, and everything. Schedule is going to be very tough. They're going to develop a system, monitor the schedule, and push, make sure that you always meet the requirement, no delay. And they always have a contingency plan to be able to make sure that your project is on schedule. Cost management is normal. You have to be understanding about the cost estimate, the budget, the control of expenditure, and try to identify all these additional work or additional issues that ask for more money. So and then are you able to supply the enough money, because your economics run is based on certain numbers, certain allowance. So you should be able to work within the allowance. Quality management is important. Risk management is become important, because risk management will help you to avoid disaster in your planning, execution, and your operation of the field. So always have to identify the risk, because of the knowledge of the oil and gas is matured field, a matured industry. We have quite a good list of risk management to be able to identify on each particular area, platform, production line, pipeline lines, processing line, processing facilities, even in terms of the corrosion issues, it's all under the risk management. And we are going to assess, mitigate, and monitor the risk and provide the solution for each one. So HSE management, HSE important. All people on field must be able to understand safety, and this work will help make sure that everybody have all this understanding that safety is important, and the field, the safeguard of the facilities is their life. Okay, contract procurement is normal to manage that the contract is all in place, and then there's no issues to really having the supply chain. Because sometimes each tender, if it is not that clear and concise, it create dispute, and then of course you delay your deliveries, and you have issues with your spare parts and so on. Stakeholder management, we have to update management in terms of what the potential of the field, any issue that we have. Negative, positive issues, share with the stakeholders. Normally, the stakeholder will have their networking, so that they will try to get some help from the experts around. So that will help you to really manage the project execution properly. Resource management for people, integration management in terms of how you coordinate if you are dealing with subsea, topside, pipeline drilling, any of the relationship between one and another, any work they want to do in terms of maintenance, it must be coordinated together, so that you reduce the amount of movement of vessels, people, so you save costs in terms of the mob demob. Change management is normal. Change management is that when we come to a new system of the work, for example, from standard to auto system, you have to know, the change of management people will change, direction will change, approval will change, with the new technology of AI and of course machine learning. Commissioning handover normally is like you mentioned before we start, we have to commission the platform. It must be done properly, identify issues, and then do all the repair before you start the production and avoid disaster. Okay, so project schedule, as you know, is going to be properly monitor. This is typical job, like this is demo concept here. Then you're talking about all this pipeline, the crane requirement for the field. Now the central processing platform, how you're going to do that, and then the design when we start, and of course the wellhead platform when we start, and so on. So it's all being prepared in parallel to make sure that the job is done in time, installation is done in time. For example, you want to have the first case use platform ready so that they can start drilling in time, so that they meet the requirement for the first gas. Okay, this is more or less the project management. Then economics is my last subject, economics. So you can see that economics you have whatever you call it, unit finding cost. Unit finding cost actually on the exploration side. Normally, some of the PSC mentioned that UFC is on your own. It's not going to be part of the calculation of unit technical cost. But in most because it is very profitable business, of course the host government will always allow you to claim your exploration cost once you are successful. You are not successful, then you bear your own cost. So oil company we have to they have to burn their budget lah to pay for this unit finding cost. If you are successful, normally FSC will allow you to put in your unit finding cost plus your unit development cost plus your unit production cost. So all these unit costs actually will be more or less defined by the total production. You have a number, and then of course unit production cost. Also, you have a total OPEX throughout the field life divided by the production cost. It become your UPC. Everything is divided by the total production over the field life. So if it is 25 years, it's going to be total production of 35 years. So for the element overview, we can see that we talk about unit cost. So the unit cost is, if it is finding cost, you add finding cost. Otherwise, it's just unit development cost by unit production cost. And you have the UTC. UTC for oil, UTC, normally in Malaysia about 30 to 40. And then for the Gulf of Mexico is 66. For US onshore, 35. Soviet offshore is 40. Canada oil deficit, of course, very slow because it's very just on mining itself. But in terms of gas, Malaysia is about 2.5. Sometimes it go to 3. The selling gas that we have is about $5 per MBTU. But some area they get a good price of $6 per MBTU for in Malaysia lah. So the offshore Gulf of Malaysia offshore is very expensive because of deep water and because of tight regulation. Onshore is about also very high because of the regulation of environment. Soviet is also very high because the extreme temperature, extreme region, right, Arctic, is very expensive. So we are lucky. I think we can produce less. We can market our gas throughout with a good profit. If we are having 10, then our field will not be economics. That's why our government is trying to find a good price to be able to get a good profit in processing and sell it at another good profit. So already have a good gain. So Malaysia, we are very lucky in terms of having quite a reasonable, gas unit technical cost. For this field, for this big field, the shale gas at field life is about this. For PSC life, about 3.7 trillion for 25 years. For example, this field, so the capex is 10, this is 10 billion, 5 billion, ringgit, it's ringgit. So divide by 4 to be able to have US dollar lah. And of course, when you talk about the US dollar MBTU, the unit cost, technical cost is about 1.25 compared to 2.5. The project is about close to about double, better than that. But this is always be the project UTC. Don't confuse with we as operator and the host government. Like I mentioned, the profit here will be divided by gas 30% for for the contractor, and government will get the 70%. I think for gas is 40% contractor, and then government will get 60%. Okay, 60 and 40. Some agreement for this big, sometimes government ask for 65 and contractor for 35. It depends on the PAC, how the profit sharing will come in. Okay. Of course, to come up with the economics, you need to have the production profile. In this field, you're talking about the 900 million cubic feet per day, for about 11 years for production. And then, of course, you have the production down because, depletion. This is going to be like maybe by 35 years, we should be producing close to about 150 million. So that's by the end. In terms of cumulative, talking about, I think there's another graph over here. This cumulative flow rate, that we have for the field. But of course, when you produce, you're going to produce water. When you go for the high flow rate, at the same time you have water in your gas flow. This is the amount of flow rate that you have, the liquid flow rate that coming in for your with your production. And this actually is adding up to your processing. If you had 900 plus, let's say 100 equivalent, it's about almost 1 trillion cubic foot of capacity required for your processing facilities. Okay, once you have that, you have to review the PSC terms and assumption. For example, equity participation, we have 90% PCSB, then you have another company, FPMV, with 10%. So the contract is 37 years for PSC, and then exploration is given within 4 years, you must develop the field. Once you discover, you must start developing after 4 years from the exploration date. Okay, production given 20 years agreement, royalty 10%, research, and then supplementary 70%. Abandonment, UOP. I have to find out what is UOP. Unit operating cost. So this is one that I talked to you. They deduct the oil. For example, the oil is $60 per barrel. They will take out about $2 from that before we share the profit. Okay. So the split is given by this is the, I think, the risk itself, RC, risk and cost lah. It depends on the range. The shilling cost for your capex, it's going to be this month. It's going to be a share, like 20%, 80, 70% share. This profit sharing between operator and the cost government, which is Petronas or government of Malaysia. So as per the economic, you have to calculate based on the Brent price, fat oil. If gas pricing is based on the budget that they have. They put a study. They have a consultant that evaluate the gas price for the next 10 years, 15 years. They use that number based on the consultant study for the gas price. And of course, energy price is 0.35. I think I'm not sure about this number. This is based on the latest 0.36 of the sale price that they have. So all these numbers here will be used to calculate the economics. So based on the cash flow, based on the assumption of the PAC, what you will have actually, you have this is the expenses what each year, how much they spend for each year before we start to have the production. So you can see that the cumulative cost here is drawn by this line. So you're getting more one line here, then add up here, we will be this line, add up. So this is cumulative, this is yearly. So you have the yearly, then you have the first gas. When you have the first gas, then you start to have earning coming back. So you start to have more and more and more for the past, let's say, 10 years for your plateau days. And then at the same time, you start to have less production. So all this is coming up with this line to call the cumulative net cash flow. And then you can see that how much you're going to be like 10, maybe the 10 trillion ringgit. 10 trillion. This is 10 trillion ringgit at the end of the 20, it's about 20 years. Agreement 20 years. So this is your profit. But remember, this is talking about project cash flow. So you have, for example, 10 trillion, but it has to be split based on the ratio. Is it going to be like 30-70 or 20-80 based on the PSC schedule that we have in terms of the volume that you produce? So all that will be cut. So in economics, for us, before we agree to really implement, normally we run again all the sensitivity analysis, what if situation. So for the what if, we're talking about, for example, the for this production, what if the production is dropped, is negative? If for example, if it's dropped by a certain percentage, then your NPV will be reducing up to, let's see here is 400 based on the P90 production. If you drop. But if you have P10, which is a good production, then you have additional, because this is the base is 712 million ringgit as our base case. But what if production is more? Then you have additional. It can go to almost like 100. So this is, which is less, then it still have a profit of the close to 400 million. So it's still within range, but this is the big impact. But what happened to gas price? If the gas price is dropping based on the market region, we can see that the impact is not much, but we can see more advantage of possible pricing from the processing gas processing plant, that the gas price when it's increasing, they can go to a better value that we can have a much more profitable income from the gas price. It's a much more sensitive lah. CapEx, if we fail to do CapEx, then the drop is there, but it's going to be a potential reduction in CapEx, because when we put a plan, we see that we're putting a lot of allowances, a lot of potential, or this high spec, whatever that demand. So based on the project itself, we can improve the CapEx, by having a better result. Okay. So all these things actually coming about. I see that. So this OPEC also the same thing. Not much impact on OPEC, but based on COPEX lah, we have to get more. So more profit. If it is CAPEX can be cut to 50% of the P50 value lah. P90 is really very not say, but P90 is talking about less likely to have, more likely to have, sorry, more likely to have, but P90, P50 is comfortable numbers, average number. So this sensitivity need to be done so that we can conclude whether and we are going to have a better result on that based on the net present value NPV. So that's what I have for for this session here. But you have any question? Then I try to answer the question. We have another bit, close to 10 minutes. Okay. Any question?
We have two questions. Okay. Okay, we have two questions. Let me see. Okay. Oh yeah, there's a question from Namira. Hi, Cikgu. Thanks for the knowledge sharing. I want to ask, what skills do we need to be eligible for this field? Is data analytics enough?
Okay, this, as you know, when we go through the I mean the requirement for personnel, we're talking about the geophysicists, geologists, and then we're talking about the reservoir engineers, drilling, production technologies. So data analytic cover all, and of course you can see that even data analytic will cover from the drilling phase, where drilling extract a lot of data, the big data system. So you're going to extract a lot of information about drilling. And then talking about the issues of drilling, the costing of it, and then the timing. So data analytic will be used to analyze those data. And like I mentioned, before we proceed with drilling, we do some analysis of offset well. Offset well normally from the nearby field, or even from the current field that we drill, exploration well or appraisal well, we have data. Then data analytic will be done to at least analyze what are the negative and positive element of the project with the data analytic, and then we have to go for planning the next campaign, and then the coming campaign of drilling. Same thing, data analytic will be important for during production. Production involve a lot of the data. Volume of data is huge. Then talking about how to manage those, of course reservoir will cover that, but data analytic will also involve with their own understanding about the trending and so on, the behavior of the field, and then of course the well itself and how it's related to the production facilities. And of course, and then when you talk about the field like, I mean, the equipment, you're talking about production facilities, you have a lot of equipment and each equipment have their own specs. It's another big data. Data analytics will be used for equipment maintenance. And of course, when you start to do the production for the well pin and A, if we go back to data analytics to understand the original condition of each well, the database of each well, and try to highlight what you want to see, what you are expected to see of each well based on the data analysis of the previous condition. That's all. It's everywhere, eh? Data analytics. Thank you.
Okay, we have one more question from Aileen. Ainin would like to ask for Kasawari operation in Miri, Sarawak Sea, is it only focusing on CCUS? Macam mana carbon is transported to Kasawari? They're curious.
Oh, Kasawari have a unique situation. When you do the study, Kasawari can install the CO2 removal on the platform, which is offshore. But because of the size, the production is huge. They have to have a very big platform installed on the platform. So the cost is huge that really make them conclude that the project is not economics. So they do another round of study. They realize that maybe they can transfer the facilities to shore, which is cheaper, and then is able to manage a wide range of possibility. For example, if they higher CO2, they can still manage. So they start to think about, planning to install the facilities onshore, which is cheaper lah. But the issue is that if you put the facility onshore, your pipeline have to be chrome or super 13% chrome or 70% chrome, which is going to be very expensive because the pipeline could be close to about 16 to 18 inches. With the kind of pressure requirement as well as the chrome, the pipeline cost is going to be also very big. So it's a very subjective situation about which ones we should go. But based on the study, they realized that it's always better to handle the facilities onshore because once you have big CO2 removal plant, the issues offshore will give you much more headache based on the OPEX. The maintenance cost will be very high. So they finally concluded based on the study and the risk analysis, having onshore will be better. So what happened? They will pump the raw gas going to pipeline, going to shore, and then, of course, from the shore, they process, remaining CO2 will be going back to the platform for injection. So that's a cycle. So they're willing to do that process. It's going to get, initially, the project is non-economical, very marginal, but with the idea of putting it on shore, they have better control on OPEX, and then they have more flexibility to have someone in the future to use their CO2 removal onshore later on. So that's the conclusion so far. Thank you.
Any more questions from the floor? Okay, Sule asks, Hi Cikgu, our AI is used in the upstream project.
AI. AI.
Okay, about AI, we have a course next week on that. So perhaps Sule, can you simpan dulu your question and ask the next trainer for the AI part?
Yeah, but I think in general, quick answer is more that AI start to really taking place in all industry. So please be able to understand AI, and because that's going to be the future game changer in the oil and gas, helping every industry, especially oil and gas, which is expensive. AI should be able to reduce our cost and manage our asset much better. Thank you.
Okay, any more questions from the participants? Okay. Okay, perhaps you can post your question. I'll do the closing remarks first. Okay, so on behalf of Taxpazman Technology, thank you everyone, and thank you Patik for your invaluable knowledge and experience on field development planning and project execution. So today we learned how multidisciplinary team work together through the FDP process from geophysical and geological studies, reservoir engineering, production engineering, development options, and all the way to project economics and execution planning. We hope you found today's session insightful and beneficial. So before you leave, please remember to complete the attendance and feedback form. I'll be posting okay, let me share. Sorry, forgot to share. Okay, so yeah, you can use the QR code over there. Okay, so your feedback is greatly appreciated and help us to improve future training sessions. So for participants who registered through the NTW portal, please ensure that you use the same name and email address that existed in the portal. Okay, as a token of our appreciation, the presentation slides will also be shared with participants who have completed the feedback form. Okay, we would like to invite you to stay connected with us. Do follow us on Fazmia Academy on LinkedIn and subscribe and follow to our YouTube channel, Fazmia Technology. In the YouTube channel, we'll be uploading our recording session soon. So for next week's session, we hope to see you again next week, 15th of July, for our next NTW session. The course title is AI in Oil and Gas. This session will be delivered by IR Razak Yaakob, the Malaysian first professional engineer, IR, in petroleum engineering, who is also not that serves as the vice president of the Institution of Engineers Malaysia, IEM, and also a board member of the Board of Engineers Malaysia, BEM. So the session has received an overwhelming response and was actually fully booked. But I'm pleased to announce that we'll be opening 50 more seats. So if you have colleagues or friends who are interested, please invite them to register while the seats are available. Go to the NTW portal to register. So that's all for today. My name is Aimi, and thank you once again for joining us. But before everyone leave, can we take a quick picture? Can everyone open your camera and I'll take a very quick capture screen capture for everyone.
Hope to see all of you coming over next week, yeah, to my talk, AI in all the oil and gas.
Yeah, here is the trainer that will be delivering the session next week.
I
Okay, so everyone, can you okay, let me change. Okay, there's like three screens, so yeah, okay. One, okay. Oh, sorry, actually there's five screen. Thank you, everyone. Okay, smile. Okay, again. Okay, next one. Smile. Okay. Yep. All right. Yes, I think I've got all. Thank you again, everyone. See you next week. Bye bye.
Thank you.